We are ready to go here. Welcome to the last session of the day. First talk will be kicked off with Holly Stewart and Peter Stelzhammer. Holly is a principal data scientist at Microsoft. She's been there for 5 years. Peter is a co-founder of AV-Comparatives. He's been there for 15 years, and they're going to give us a talk today on prevalence-weighted anti-malware testing. Take it away.
Thank you. I'll kind of give you guys a quick overview of what we're going to talk about today. What we want to discuss is a new model for scoring vendors in anti-malware tests. And we want to look at customer impact and factor that into the test score so that a vendor's test score really, as accurately as possible, reflects what would happen in the real world with real customers, true customer impact. The way that we are measuring impact is by doing a couple things. So first of all, we're only looking at true malware samples, the really bad stuff. So we don't look at things like adware, potentially unwanted software, other things that would likely be disputed in a test, but truly the worst category of malware that pretty much everyone agrees shouldn't be on anyone's computer. The second thing that we're looking at is the prevalence of that malware, and that's where the model really comes into play. How do you take prevalence of a file or a family or other information about a malware group or category and translate that into a model and a test score that really represents the customer impact? We've got a couple different models that we'll go through with you today. And we'll talk about a lot of the constraints, because coming up with this kind of model, it's really difficult. So for example, take a malware family that is highly polymorphic. And one sample within that family has an impact, a customer impact of 1, because only one customer gets served that specific malware sample. You may never have telemetry from that sample. Maybe a vendor reported that sample to AV-Comparatives, but they weren't willing to provide the telemetry that comes with that sample. So how do you model that? How do you score that when there's a really prevalent malware family, but the sample that you tested only has an impact of 1? And what do you do when you don't have any telemetry at all? We'll talk about some of those constraints. Then we'll go through the models that we came up with, and also show you some of the test results and some actions that we think as a community we should move forward with.
Yeah. You will be wondered how the test results are looking like. You may expect a great diversity, but yeah, be surprised.
So let's take a really simple model to clarify what we're talking about here. Let's say we had only 10 samples in a test set. In a traditional scoring model, each of those samples would count for 10%. But if you took those 10 samples and you looked at how many customers they actually impacted, you might find that one of those samples was incredibly prevalent. 60% of all the telemetry revolved around one of those samples. The next highly prevalent one represents another 10%. And you go down to the last sample, which might have 0.0001% impact, right? So if you look at the customer impact, if a vendor had missed one of those samples, clearly, if they missed a highly prevalent sample, there would be a much greater customer impact than if they had missed one of the least prevalent ones. So the model that we're talking about is really just accurately representing that prevalence model and putting it into the scoring system. Another one of the difficulties is the ecosystem itself. This shows data from March earlier this year, and it ranks malware families by the most prevalent malware families all the way to the least prevalent families. So it's a long-tail distribution system, meaning that most of the impact comes in the very head of the curve, the very top of the curve. And there's a very small number of families that fit into that curve. But if you look at the total number of malware families that were in the ecosystem in that month, and we're not talking about exploits, we're not talking about potentially unwanted, we're just talking about that pretty small set of malware families that we all agree are truly impactful and bad for customers to have. There were about 5,000 different malware families, and that represented 4.6 million files. So There's a lot of diversity within those malware families, so there's a lot of variance. And when you have lots of variance like that, it means your model and your test set has to be super strong to be able to accommodate that kind of variance within your sample selection set. And obviously, the testers can't test the ecosystem. You have 4.6 million files. There's no system I've seen that can scale to actually fully represent the ecosystem during a given month. There's a couple of other constraints that Peter will talk about, and I'll provide some color.
Yeah, there are some other constraints. What we try to do in our tests is we need to put on only indisputable files. So we have to look that there is no adware or potential unwanted applications in there, that it's really malicious. There are no keyloggers or legal keyloggers, because this leads to some arguments with the vendors. And the thing is that the number of new samples available that match that criteria is really limited. For example, also Jenks's was one of the most prevalent families in March 2015. The most prevalent component was not a PE file, it was only a script component. In fact, Microsoft only saw 12 new PE files for Jenks's leading up to the test. The test was done in March with around about 131,000 files, which is a huge base, but it cannot really reflect the whole ecosystem. So this demonstrates the scarcity of the samples, especially for certain families that propagate through non-PE components. That's a huge problem. And in this world, with a daily churn of hundreds of thousands of new malicious files per day, combined with limited access to those files, testers need really to rely on sampled versions of the real world with a bias toward malware that lends itself to being collected and tested. And that's really not an easy task. To solve this situation, as it often happens in statistics, we really need to try to create a model that best represents the real world. So if you have a look at the files itself, the recently discovered files have been only 23% in the past 30 days. And by Microsoft, not even all of the files have been obtainable. Maybe you can speak a little more in detail to the counts.
Sure. So a lot of vendors like us, when we detect a file, we don't request that sample. So the samples we request tend to be the things we don't detect yet. So we've got some early warning telemetry that says that a file is suspicious. We request those files, we grab those files, and we look at those files and we add detection. For the files that we already detect, we don't need those. But for a tester, when they are putting together their sample collection, they need the files that everyone detects. So it's often difficult to get a source, a number of samples to that matches what we've actually seen in the ecosystem that month. But look at 4% may come from us. Obviously, testers to build a diverse test set are going to source samples from many different locations. But still, that represents 23% of all the customer impact that we saw in that month. The new files, PE files that we're seeing versus all of the other file types and the old components, which we still see in the ecosystem, far outweigh this new PE group.
Yeah, and leading up to the test, as I explained before, Microsoft only saw 12 files for Jenks's, and we at AV-Comparatives have seen even much more of it.
So let's have a look at the different models that we have evaluated. The first one is really simple. You take a file that's in the test set, and you look at the customer prevalence of that file. So how many distinct computers reported that file, either through unknown telemetry or through confirmed detections throughout a certain time period. Then you weight that across all the files that are in the test set, and the prevalence of those files. And the number of files that you miss become what is deducted from your test score, and the files that are in the total test set are your denominator. Pretty simple method. However, when we looked at this model and we compared it to the ecosystem, we saw that there was a lot of discrepancies. It just didn't fit the ecosystem curve. And it mainly applied to really highly prevalent malware families. So in this chart, it looks purple here. It's dark blue on my computer. This purple bar represents the ecosystem, so the family prevalence of the ecosystem, and then that teal bar is how this new model represented itself within this test scoring paradigm. And as you see, a lot of the prevalent families were severely underrepresented. Some of the families that had a lot of samples and high prevalence, like Dorkbot and Upatre, were overrepresented. Then, so that's sort of the high prevalence families. If you look at the moderate, low, and very low, there's also some discrepancies there. This model clearly doesn't fit the ecosystem curve. So we tried again.
And again.
Yeah, and again. So the next thing we started looking at is the family prevalence. So why not just take the sample prevalence alone, view that in context of the overall prevalence of the malware family? And we looked at two different models. The first model upgrades or downgrades the prevalence of a sample based on the prevalence of the malware family. So if you have a sample that affected 10 customers in a highly prevalent family, that sample counts more than a sample that also affected 10 customers, but is in a really tiny family. The second family model that we looked at basically would force fit the samples of a particular family to the ecosystem curve. So if the family in the ecosystem represented 20% of all the malware encounters that people had in that time period, then the test score for that sample set also represents 20%. Let's talk about the next slide, and it shows the results of these two models. So the first model is on your left. This is the upgrade-downgrade model, and you can see that clearly many of the families did not fit the ecosystem curve in this model. Several families are highly overrepresented, and some are severely underrepresented. And it really depended on the mix of the test set and how many samples were represented for each malware family. So the next model that we tried was force-fitting the score of the samples in a particular family to the prevalence of the family itself. That's this next one on your right. And that one looks fantastic on paper. You see that the teal lines match up very well with the purple lines. However, when you look really closely at the scores, if the tester, for example, had only selected a small number of files for one of the families, and I think the examples here were Brontok and Dorkbot, those few samples in that test set represented a huge portion of the test score. So if a vendor happened to just miss a couple of those files, their test score would be severely impacted, even though there really weren't that many samples in the test set. What we realized is that that model, although it looks really good on paper, puts a lot of constraints on the tester. They would have to have a perfect statistical model for every family that was in the test. And with the constraints that we talked about, new files, PE files, samples that people were able to obtain, this model really wasn't feasible. It wasn't going to work in any kind of practical sense. So we tried again. So this last model that we tried incorporates file prevalence, family prevalence, and what we're calling partition prevalence. So you guys saw some of those families that were grouped into a high, moderate, low, very low partition. Rather than trying to force fit all the samples in a particular family to meet that ecosystem curve, we force fit the group of families. This means that the tester doesn't have to do an absolutely perfect job in selecting a statistically relevant set for each of the families. They just need to focus on the general category families: highly prevalent, moderately prevalent, low, and very low. This is a much more reasonable approach. Oh, and a big call out to Fanny of École Polytechnique of Montreal. I don't know if she's in here, but hi. Thanks for the head-tail breaks method. It worked very well. So what we did to come up with those categories is we used this head-tail breaks method to create the high, you can look it up, it's pretty standard statistical model, the high, moderate, low, and very low families. And when you use this kind of model, you'll see that the high category, for example, there were 15 families in that. But those 15 families represent 48% of the entire ecosystem impact. It's pretty huge. So we use that to rank to create the test scores and apply that to the end result, the family, the sample prevalence, and this category. So the model is still not a perfect fit. And if you look at the distinct families, you'll see that the family ecosystem prevalence still does not exactly match what the test score, prevalence score would reflect. However, when you group those families into the high category, it does perfectly match, because the nice thing about this model is that it force fits everything that's in high, everything that's in moderate and low to the ecosystem curve. So your test score will represent what the ecosystem has been impacted by.
Good. Let's come to the results we have seen. We have done the table where you can see the vendor ranking with the traditional model and the vendor ranking with the prevalence model we used, and the movement. What you can see here is a movement between the middle field, but what you can see also is that the top vendors stay on top, even if you use the traditional model or if you use the prevalence model, and the vendors with a not so good detection are staying on the bottom. So it's mostly in the middle field that there are some shifts to the top or to the lower end. The thing what we have seen is the highest and the lowest score are really going in another way. On the traditional model, the highest score was 99.96%, and the lowest score was 86%. By using the prevalence model, the ranking was much more closer because of the prevalence stuff. So it's for us much more difficult to show the stuff, the stuff how they are different in detection. And if you have a look at the three vendors that which did significantly worse using the new model, all had more misses than their formerly closely and ranked peers in highly prevalent families. You can see this at Kilim or Gamaru, Changsuz, or also at Bladabindi. Those misses drove their test scores really down. That's the most impressive part. If we have a look at another table, if we look of the global vendor ranking and the regional detection score, which is very, very interesting. So you can see that the top vendors are detecting in each country, and each geolocation very good. But if you look at the vendors which are not so good in detection, they are missing in other geographical locations. So some vendors in the top 5 had really very localized results, performing very well in certain regions, like Brazil, China, Colombia, Egypt, and Korea. And the other vendors performing in the middle of the global test had really high scores for certain regions: Canada, Indonesia, Russia, Ukraine, and the US. So this difference could indicate that there is some market bias for detection, and that you can see here in the table. Yeah, going forward.
So we learned quite a few things from creating these models, and I think one of the most important things that we learned is that it's nearly impossible to take a traditional scoring model and have it represent the ecosystem, because to try to source the vast number of PE files that you would need to fill out certain categories for some families, it's not technically feasible. So adding this layer of prevalence significantly improves the accuracy of the test score. We also learned that building a good model is really complicated. It took us lots of iterations to go through all of these different models and look at the scores and decide, does this look fair? Does this seem fair? And create these calculations to come up with the model we finally landed on. And it's by far not perfect. I know that we will continue to evolve and make this better as we learn more and we try new things. And I think the other thing that we learned, to what Peter was just saying, is that the the detailed local information, the local prevalence information is really interesting. So as you saw, some vendors are really good on a global basis. So if you're a corporate customer and you have employees who work in all parts of the world, you're going to want to choose a vendor who's very strong globally. Or if you are a consumer and you're in one particular country, you may want to know who's really strong in your market and choose that vendor to ensure that they're going to protect you against the threats that are most relevant in your ecosystem. So I think those results were super interesting, and hopefully we can get more vendors to contribute that kind of detailed information so we can build out our model and make it better.
Make it more accurate, yeah. So what we really would like to see is to make this model work and avoid bias, we need more vendors to submit telemetry data. We cannot rely only on the telemetry data of some vendors. We're getting a lot of telemetry data from vendors and also from Microsoft, of course, but we need more to make this more accurate. So we need consistent and reporting methodology. So we need to have a look at distinct machines, family prevalence, common time frames, and locality-specific data. That would be ideal. So one of the approaches is already done by AMTSO, the Anti-Malware Testing Standard Organization, with the real-time threat list, the RTTL. And it looks good. There is a meeting in October where someone will go forward in that case. But for this, we really need more vendors submitting more and more data that we can rely on the status. And there should be more accuracy of prevalence data of files, families and locality, so that the reporting should be more a summary.
Oh. Yeah. Okay, do we have any questions? Wait, please wait for the mic.
Microphone. He's coming.
On the data where you show the rank shifting among the various vendors, that was for a particular month, right? That was for 1 month of testing?
That was for one test. This model was run for the March test in 2015, based on 130,001 samples in our test bed. Right. And before you ask, Microsoft is not in there.
Okay. So, but they're all tested for the threat landscape as it existed in March of 2015.
Yes.
That's right.
So no matter how many samples you use, if you now look at April and May and June as the threat landscape changes, and then look at these results, some of these patterns, you should be able to see, some of your conclusions would be, you get a lot more insight
right.
if you look at separate months, because now you can correct for the noise of the representation of particular samples in particular families and that sort of thing.
You would want samples that are relevant for the time period in which you do the test and in which you prevalence weight them. So you would want to follow, so for example, in the next month, if Jinxkis went really down in prevalence, or it changed its model, so it was using different types of files to infect people, then you'd obviously want to adjust your model and only rank, create a new methodology for your sample selection set, and then prevalence weight the impact based on the prevalence of those families that month. But yes, it would be interesting to trend the results. It's not something we've done yet.
Yes, okay.
Any other questions? Oh, right here.
I have a question. How do you verify suspicious samples that come to you from vendors, for example, with generic verdicts? And how do you recognize to which family this sample belongs? That classification problem is hard, actually.
That's a great question. And we work really hard at doing that, in fact. So with the test sets that we've looked at, Andreas has a lot of algorithms to do some clustering. Oftentimes, we'll just apply brute manpower to look at the samples and get them properly classified. And then for the things that we can't, that are in that long tail, we actually apply an average family prevalence weight to those because they're not classifiable, but they should still count because they're in that long tail. So that's how we've handled the cases that we haven't been able to get to classify.
Okay. And did I get you correctly? You solved the problem of polymorphic samples using this prevalence for families?
So for polymorphic samples, what we do, if we don't have telemetry for that, we assume there's always a telemetry of 1. And then we rank the highly polymorphic families according to the family prevalence. So if I have a family prevalence of 100,000, it's going to be ranked much higher than a family prevalence of something that's, 1,000. And then that partition prevalence also applies. So if I'm in the high category family, again, you get a second bump for being in the high category families rather than in the tail.
Thank you.
I'd like to ask one question about your family definition. Is it based on Microsoft signature names, or is it based on several vendors' signature names, or is it something different?
So we do everything we can to get the proper classification. The first classification we look at is our Microsoft signature name. Then Andreas and team also send what their family classification is. We've got a lot of heuristic mechanisms that also apply classification. So if it's detected by one of our generic families, we've actually got this very complex prioritization model where we look at first Microsoft family name if it's a real family, not generic. Second, what Andreas said it was. Third, our generic, we have several different generic algorithms that categorize it into families. So we've got, quite a long list. And honestly, I would love to add more context into that model. So if you happen to be really good at classifying certain types of families, it would be fantastic. This comes back to sharing telemetry and information to make this model better. It would be great to get that from GData and pull that into the model so that we do even better classification of the samples that are in there.
Yeah, to really improve the model, it's important that we're getting more and more data. That's really based on data, telemetry data. And we would like to see more vendors putting in more data in the telemetry stuff. That would be really a good thing.
Will AVC consider to apply this model or similar model to Android test?
To Android,
Android
a
test.
similar model to Android test. At this time, we don't have the data for it, but if we would have the data, it would be possible. We at AV-Comparatives are doing already a detection and behavior test of Android APKs, but at this time, there's not such a prevalence model, but it would be a good thing to do that, yeah. Maybe we can ask Google to help us for that.
I have one question for you. When you applied the new scoring model, the range between the highest score and the lowest score narrowed considerably. Do you have any concerns about stack ranking products based on such a narrow window of percentage differences?
Indeed, we have. So we have to look what we can do with that. Because of the clustering, what we are doing with the Eugene clusters, it will get more and more difficult. Because as the more wider the vendors, the results are spread, the easier it is. But the closer they are, that more difficult it gets.
And it depends on the scale too, right? If you apply the scale so that you show the top and the bottom, your graph is going to show who is significantly better than others when it comes to prevalence. So you can change the scale and the way that it's presented so that you can still see the differences.
Okay.
So I just want to say a big thank you to AV-Comparatives. They've been working with us for a long time on this model, and I have a lot of respect for the work that they put into selecting their test set, and so thanks, Peter, for working with us so closely on this.
Yeah. Thank you, Holly. It was really impressive, the huge database to see which Microsoft has about that stuff. That's really impressive.
Okay. Let's thank our speakers, Holly and Peter.